All right, so section 2.4, parent functions and transformations thereof. So what do you know about a parent function? What is a parent function? Parent function. What's a function? Yeah, something that passes the vertical line test, right? And of course, you can't say function without saying the word ction or fun, right? So functions have fun built right into them. And a parent, we all know what a parent is, right? You got a mother and a father, so you can call these father functions or mother functions if you want. Just be careful how you say that one. But from these parent functions or mother functions come other functions. And what we're going to be doing is memorizing kind of a cast of parent functions right here. Some of these you're already familiar with. And then we're going to look at how a change in the equation will manifest on the graph. And it should be the same manifestation for all graphs. It just depends what you're starting with. So these are the basic parent functions right now for which you're responsible. You got your classic polynomial parent functions, f of x equals x, x squared, and x cubed. So we got two odd degree functions, x and x cubed. Notice they look very similar, except x cubed is a little wigglier. But they both pass through the origin. They're both monotonic increasing. Then we got of course, the parabola. Then we got the square root of x function. That is half of the parabola turned sideways, opening up. We've got the 1 over x function, which we've seen quite a bit already this year. So the ones that we haven't really seen this year, maybe the absolute value of x function. That's just the line y equals x to the right, and it's the line y equals negative x to the left. So it makes this little v at the origin. So it kind of looks like the parabola, except it's straight lines. It's got a vertex at 0, 0. But these are the two right here that might be new to you. The one on the left is the parent exponential function. So an exponential function has a horizontal asymptote on the x-axis. As you go to the left, as x goes to negative infinity, these always approach 0. And probably the most basic exponential function that you have experience with is like 2 to the x. It's like cell division, mitosis, meiosis. So that would be something that doubles every cycle, times 2, times 2, times 2. Well, we're going to use the natural base e. E is about 2.718. And it's the second most famous irrational number in all of mathematics. So anytime you have a base, in general, they're of this form, b to the x power. The base is some number, and the variable is the exponent. If the base is greater than 1, you have exponential growth. If your base is between 0 and 1, like if you've ever studied like half-lives of radioactive isotopes, you have a decay function. We call it exponential decay. So E is not the letter E from your English class. E is the number E, and it's between 2 and 3. It's an irrational number. So it's a non-terminating, non-repeating decimal. And because 2.7 is greater than 1, this is exponential growth. So it passes through the y-axis at what point? How can you find the y-intercept of e to the x, or any function? Yeah, plug in a 0 for x, right? So e to the 0, or 2 to the 0, or 5 to the 0, what's e to the 0? 1, right. Anything to the 0 except 0 is 1. E to the 0 is 1, 2 to the 0 is 1. So this has a y-intercept at 0, 1. So the domain is all real numbers. The range is everything strictly greater than 0. It's a monotonic increasing function. And it gets pretty big pretty fast. These things grow rapidly for large values of x, faster than x squared, faster than x cubed. All right, so the inverse function of any exponential function is a log function. Exponentials and logs are inverses of each other, like multiplication and division are inverses. So the inverse function of the exponential function e to the x is log base e to the x, and we call that the natural log function. And we write it as ln of x. So you studied log functions in Algebra 2. They were of this form, y equals log base b of x. And you probably studied them right after exponentials. Okay? So when we write the natural log of x, this is equivalent to log base e of x. Log base e of x we call the natural log because e is called the natural base. Now you've already seen probably in your science class this log. If you see log but you don't see a subscript here for the base, of course you know that to be implied base what? 10, right. This is called the common log or the common base. It's the scientific base. Scientists use base 10. Mathematicians like to use base e. So when we take base e, we call it the natural log of x. And it is the, again, inverse of e to the x. So what happens when you have an inverse is all the x and y information interchange. So because e to the x has a y-intercept at 0, 1, the natural log of x has an x-intercept at 1, 0. We change the ordered pair. 0, 1 becomes 1, 0. The x-axis, where we had a horizontal asymptote, becomes the y-axis, where now we have a vertical asymptote. So the natural log of x has a vertical asymptote on the x-axis. This function is still monotonically increasing, just like e to the x. The domain of the e to the x was all real numbers. That's now the range of the natural log of x. The range of e to the x was everything greater than 0. That's now the domain of the natural log of x. So all the x and y information from e to the x and ln of x interchange. They're inverses of each other. So memorize those shapes, and we can start graphing transformations of them. So right now we have these 8, and we will pick up some more as the year goes on. All right, so example 1. Here's a chance, bless you, to try out some of the new skills we have combined with kind of an old skill from earlier in the year. Sketch the following piecewise function. Check for domain and range, continuity, relative extrema, symmetry, all that good stuff we learned in the previous section. All right, so this is like a 4-headed beast, right? Piecewise function. 4 different pieces. What's the first thing that you would do if you were tasked with sketching a piecewise function like this? Draw a graph? How? We're going to need an x and y axis, so if you have no other idea what to do, go ahead and draw yourself an x and y axis. Then how do we draw a graph? We pick a color, and then we start drawing. Something like that. I don't know. That doesn't even pass the vertical line test. Shame on me. You look at the pieces themselves. This is part line, part parabola, part radical function, and x to the negative first. Is that a parent function? Yes, it is. Because remember, we studied negative exponents at length already this year. X to the negative first is the same as what? 1 over x. Yeah, x to the negative first is the same as 1 over x to the positive first. And that is our parent function, Mr. Reciprocal Man. So we know, we recognize all the pieces. Now we just have to sketch those parts of the graph on the intervals where they are defined. So this is where the limits come in. The most important x values on this entire graph are what? What are the most important x values? -1, good, where it changes from line to parabola. 0, where it changes from parabola to radical man. And 1, where it changes from radical dude to reciprocal dude. All right, so we're going to go ahead and put those marks down on our graph. Here's -1. There's, of course, 0. And here's +1. I'm going to move this down a little bit just to give myself more vertical freedom here. And maybe extend the y-axis up and down. All right, so now this is where the limits come in. I want to know what is the limit as x approaches -1 from the left. Well, left of -1 is less than -1. What do you get when you plug in a -1 for x? -1, right? Now, because it's equal to, that's also the function value. So at -1, -1, we are putting a what? Solid dot, open circle, or another tree? Solid dot. Good, right there. Solid dot. Now, everywhere to the left of -1, it looks like x. So let's go ahead and draw what it looks like coming in. The graph of y equals x, remember, would pass through the origin. So even though you need 2 points for a graph and we only have 1, you can kind of use the origin as your second point. But you're not going to draw it to the right of -1. So you're just going to draw a line coming in like that, as if it would go through the origin if you were to keep it going. All right, we got one of the 4 pieces done. That means 3 pieces left to go. It's like we've been to the Magic Kingdom and there's still 3 other parks to go to. Yes. All right, so now between -1 and 0, we have x squared. What is the limit from the right of -1? Right of -1 is greater than -1. Remember, you read this as x is greater than -1. So by direct substitution, you get a what? +1. Good. So at -1, +1, we put a what? Open circle, solid dot. Open circle. So -1, 1. Here we come. -1, 1. There's 1 right there. We put an open circle. And then we want to know what is the limit as we approach 0 from the left. Left of 0 is less than 0. By direct substitution, you get 0 squared, which is 0. Solid or open? Sopen. Right. Good. There we go. So now we have the starting point for this piece, the ending point for that piece. We connect it with a parabola piece. Now this would normally bounce at the origin and go up. So there's that piece right there. Sweet. All right, so we've been to the Magic Kingdom. We just went to Epcot. There's still 2 parks left, 2 pieces left. We got the square root of x, which is like, I guess, Hollywood Studios. What's the limit from the right of 0? Right of 0 is greater than 0. Plug it in, you get 0. Solid or open? Solid. So at the origin, we put a. How do we put a solid dot at the origin if there's already an open circle? Just fill it in, right? Yay. And now we need the limit from the left of 1. The limit from the left of 1, hey, come back. The limit from the left of 1 is less than 1, less than 1. Direct substitution, square root of 1. 1. Solid or open at 1, 1? Open, all right, 1, 1, open. Now we connect it with a piece of the radical dude graph, which remember comes out of the origin like that. Actually, almost vertical first. There we go, more like that. It's the sideways parabola. I actually kind of went into the hole. Let's do it again. There we go. Much better. All right. We got 3 of the 4 pieces done. There's 1 park left. That's the Animal Kingdom. What do we do? How do we sketch that piece? Limit from the right of 1. Direct sub. What do you get? What's 1 to the negative first? -1? Nope. It's 1. Because remember, 1 to the negative first is the reciprocal of 1. What's the reciprocal of 1? 1. Yeah. Solid or open at 1, 1? Open. Okay. There it is. Well, it's already open, so I guess I'll just trace on top of the open. Now it's double open. Now, everywhere to the right of 1, it looks like 1 over x. Do we know what the graph of 1 over x looks like to the right of 1? Yeah, well, there's 1 right there. We just draw it looking like that. So remember, this one has a horizontal asymptote, so we draw it approaching the x-axis. And we'll go ahead and draw a little dotted line there. And there it is. There's the beautiful piecewise function that's made up of 4 of your 8 parent functions. Does it pass the vertical line test? Yeah, sure does. Let's go ahead and find the domain now. What is the domain of, this guy's name is G, like Goofy. What is the domain of G? Is it all real numbers? X doesn't equal 1, so it's a set of all x such that x is not 1. Right, the 1 over x had a built-in discontinuity at 0, but we don't see the vertical asymptote because we're starting it at 1. But based upon the definition of the piecewise function, there was no equal sign at 1. And it looks like from left to right, every other x value has a dot or a part of the graph, so that's good. The range of G. Remember, ranges we get from the graph. So we look for the y values. Come in from the bottom here. That arrow means that it goes down to negative infinity. So we get all the y values from negative infinity. We get the y value at -1. That's good. Do we get any y values between -1 and 0? Is that covered anywhere between -1 and 0? No, it looks like we have a gap there. So let's go ahead. If you want to do it in set notation, it would be the set of all y's such that y is less than or equal to -1, or now it looks like I pick up 0, and I get all the values from 0 to 1. Do I actually get y equals 1 anywhere? Nope. And do I get anything above 1? No. So now I get all the y values between 0 inclusive and 1 non-inclusive. So we write that as a compound inequality. We say 0 less than or equal to y less than 1. So that's how you do it with inequalities. Or you can use interval notation, right? Negative infinity to negative 1 beefy bracket. Union beefy bracket 0 to 1 parentheses. However you like to do it. All right, so that's domain range. Continuity, is this function continuous? No, it's got some obvious discontinuities. The first one is at negative 1. The limit from the left is negative 1. The limit from the right is positive 1. What type of discontinuity do we have there? A jump. All right, so we have a jump. Remember, we say the jump is at x equals. We don't list the y values because there's two different ones. Remember, for the jump, it doesn't matter where the function value is. Some people are still confused about that. The function value can plug one of the holes, or it could be somewhere else, or it could just be non-existent. The jump exists when the limit from the left and the limit from the right, that is the two roads, go to two different y values. If they were both open, it would not be a vertical asymptote. Vertical asymptotes force your y values to infinity or negative infinity. Here the y values are approaching negative 1 and 1. All right, at 0, we actually have a continuous function right there. At 1, though, we have a what? A hole, yeah. So we have a hole or removable point discontinuity at 1, 1. That's the only one that we list as an ordered pair. Even if the function was explicitly defined somewhere else to be like that, we would still have a hole at 1, 1. All right, and I think that's it. This runs out to the right forever and ever and ever. The horizontal asymptote is not a discontinuity. It's just an end behavior asymptote. Do we have any local extrema? Local extrema, local max or local min. Is this negative 1 right here a local max or a local min, or neither? It's neither, right. To the left we have lower, to the right we have higher, so that's a neither. Right here at 0, 0, is y equals 0 a local max, min, or neither? That's a local min, good. So we have a local min, let's write that, local min of 0 at 0. And notice I didn't put y equals or x equals there. You really don't have to. If you want to clarify, you certainly can. But remember, when we say of, we mean the y value. And when we say at, we mean the x value. It's implied. What about at 1? At 1, 1, do we have a local max, min, or neither? Neither. Good. There's not even a function value there to talk about. So we don't say the open hole is a local max because there's no point there. So what's the point of talking about a local max if there's no point? Literally, there's no point to it. Anything else going to the right? Any local max mins? Is 0 a local min here since we're approaching 0? No, not a local min. All right, now the last thing it says is symmetry. Does this graph have any symmetry? Y-axis? I don't think so. Origin? Turn it upside down, is it the same? Not even. No, so no symmetry. No symmetry. So there you go. Awesome. Y'all are getting good at this already. So it says now we're comfortable with these 8 parent functions. Let's play with them a little by changing a thing or two in their equations. All right, so whenever you're going to sketch a transformation of a parent function, the first thing you want to do when you see the equation is to identify the parent function so that you know what the original shape is of the graph you're working with. Then you're going to put the function in what I call standard transformation form. Standard meaning if you do it every time, you can kind of look at the equation and predict how the changes are going to manifest on the graph. And then you're going to sketch the function using your dear Aunt Sally's rules. Please excuse my dear Aunt Sally. Okay? So here's what standard transformation form looks like. A function g of x, the transform function g of x, instead of being written in standard transformation form, if it's written like this. So say we start with the parent function y equals f of x. Okay, so you can see f right there. It's going to be a times f of b times x minus c, close, plus d. A, B, C, and D. Okay, that's in alphabetical order. It's also from left to right. It also is in the correct order of your Dear Aunt Sally's rules. Notice A and B are being multiplied, whereas C and D are being added and or subtracted. And your Aunt Sally says to do multiplication and division before addition and subtraction. So if you can write every equation in this form, you can actually implement the transformations then from left to right. All right, so here's what we're going to have. The A and the B, since they're multiplied, anytime you multiply something, you're going to be dilating it. You're making it twice as big, 3 times as big, 4 times as big. So let me write that again. That looks like a different word. These are multiplied. That means they're going to be dilations. Now, a dilation is a generic term. What we're going to be saying is they're either stretched, which means make it bigger, or they're compressed. So those are directional words, kind of like vectors, stretched or compressed. The C and the D are both added or subtracted. Anytime you add or subtract something, you are not dilating, you are just translating, or I'll use the word shifting. You're shifting. And these are going to be either shifted right or shifted left, or up or down. Those are the only directions we're allowed to shift, one of 4 directions, left, right, up, or down. So stretching, compressing, and then left, right, up, or down. So that's the first dynamic you need to understand. Is the number in the equation being multiplied or is it being added? Is it being divided or is it being subtracted? Multiply and divide are the same. Addition and subtract are the same. That's the first dynamic. The other dynamic that's important to recognize, and I'll shift flavors here, are the following. If you look at the A and the D are outside the function. The function, remember, is f of x. So here's the f of part. The A is outside, the D is outside. Anything that's outside the function is affecting the y values. Because you remember the way you evaluate a function is you pick your independent variable, you drop it into the function, and then you get your y values. So in this case, we're picking an x, we're dropping it into the function f of x, and we're getting an output, and we're changing the outputs. Outside the function is changing the outputs. It changes the y values. Whereas if you look at the B and the C, I'll do it like this. The B and the C are inside the function. And if you're getting some values surrounding the x on the inside of the function, you're changing the graph's x values, or horizontally, okay? So outside, you're affecting the graph vertically, in other words, the y values. Inside, you're affecting the graph horizontally. You're affecting the x values. So now if you can combine those two dynamics, you'll know exactly what you're doing. A, then, is going to be a vertical stretch or compression. B is going to be a horizontal stretch or compression. C is a horizontal shift, left or right. And D is a vertical shift, up or down. Okay? Now, there's one other thing that A and B can do. You have something called a negative dilation. If A is negative and B is negative, those are going to be reflections. All right? If A is negative, it's going to be a vertical reflection, which means the y values are changing. So that's across the x-axis. If B is negative, it's a horizontal reflection. Your x values are changing across the y-axis. Okay? So all that is pretty much restated down below for your convenience if you want to read through that. I'm ready to try it out. Example 3. For the following function, identify the parent function, write the equation in standard transformation form, and then we'll sketch the graph. Okay, so you walk up to the function. You're like, what's up, H? I know who your daddy is, or I know who your mother is. I know both your parents. Who are they? Or what is it? What's the parent function here? square root of x, right? You either look for a 1/2 exponent, or in this case, you see a square root and the x is underneath there. So we're starting with this guy right here. Now, you don't have to draw this, but that's what we're starting with. You're envisioning that right there. Now that we identified the parent function, we need to put it in the standard transformation form. This thing is not in standard transformation form. The 3 that you encounter first is actually being added outside the function. In this case, to be outside the function means to be outside the radical. So that's your d value, so he goes to the back. The 1/2 is being multiplied in the front. So the first thing I'm going to do is just do that. I took care of my a and the d. The a is going to be 1/2, the d is going to be plus 3. Outside the radical, multiplied, added. If there's ever going to be a lot of work to do, it's going to be on the inside. Because on the inside of the function, here's what we need. We need the x term to be first, and then the most important thing is inside the function, we need the exponent of that x, or the, not exponent, sorry. We need the coefficient of the x to be a 1. If that coefficient of x is not 1, you have to factor out whatever it is from both of those terms and call that thing b. Okay, so it's b times 1x minus c. So let's look at what we have here. First things first, my x term is not written first, is it? It's second. So I'm going to do this in baby steps. And if you want to do it in big adult steps, that's fine, just don't mess up. All right, so all I did on that line is I commuted the terms under the radical. I wrote the x term first. Notice it's still negative. It's just now in the front. Now the all-important question. You look at the number in front of the x and you ask yourself, self, is that a 1? Is negative 4 equal to 1? Nope. So what you have to do now is factor out whatever that number is. But you're still on the inside of the function. You got to factor out inside the function. So I'm going to factor out my negative 4 and put parentheses. So when you factor a negative 4 out of itself, you're left with a 1x. There you go. Perfect. Now you just got to divide the negative 4 out of the 2. What do you get when you divide a negative 4 out of a 2? What's 2 divided by negative 4? Negative 2/4 or 1/2. Yeah. Remember, factoring out is dividing out. So it's what you started with divided by what you factored out. Now, real quickly at this point, mentally redistribute it and make sure you have this above. Negative 4 times x is negative 4x. Go us. Negative 4 times negative 1/2, positive 2. Heck yeah, we got it. And then we have our plus 3. If you don't factor out that number in front of the x, you're going to get your horizontal shift wrong, okay? Which means you're going to get the whole thing wrong. That's kind of embarrassing. All right, so this is your a value. This is your b value. This is your c value. And that's your d value. So I might ask you to describe the sequence of transformations. You have to perform the sequence of transformations in the order your Aunt Sally insists upon. Which again, if you write it in standard transformation form, you're set up to do it from left to right. Because it's multiplication first and then addition, subtraction second. So here's what we're going to do. To our parent function square root of x, we're going to do the following. The 1/2 is going to be a vertical, and because it's going to be half as tall as it used to be, the y values are half of what they used to be. So a 4 is now a 2. A 9 is now a 4.5. If it's half as tall, are we compressing it or stretching it? We're compressing it. We're vertically compressing, and I'm going to abbreviate compression like that, by a factor of. You can abbreviate by a factor of as BFO, BFO, by a factor of. Now, is it by a factor of 1/2 or by a factor of 2? Yes, it's by a factor of 2. When you're compressing something, you're making it twice as compressed, which means half as tall. So compression means getting smaller. You're compressing it by a factor of 2. In fact, anytime you say by a factor of, that number there, right there, let's just say this. In general, when you say by a factor of a better be greater than 1. If you ever say by a factor of 1/2, you got to be careful because that could be like a double negative. So if your number is already less than 1, like 1/2, just put the reciprocal of it right there. half as tall means compressed by a factor of 2. Perfect. Now we go inside. The negative in front of the b is its own transformation. If a and b are negative, it's their own thing. The x values now are the opposite of what they used to be. So a positive x and a negative x are switching places. Negative 4 and positive 4 switch across the what axis? When x's switch places, they do so across the y-axis. So we're going to have a y-axis reflection. If you have a negative b value, it's going to be a y-axis reflection. Your x's, because it's on the inside with the x, are going to be the opposite. The 4 then is going to be a horizontal what? It looks like it's going to be a stretch, right? 4 times x, 4 times the width. But here's the deal that you might have learned in Algebra 2. Everything on the inside is going to be the opposite of what it appears. So it looks like 4 times x, 4 times wider. It's actually 4 times narrower. So this is going to be a horizontal compression, by a factor of 4. Again, anytime you say by the factor of, that number's got to be bigger than 1. So it's 4 times narrower, not 4 times wider. Now that takes care of the dilations and reflections, which are the multiplier things. Let's come over here and kind of list the next sequence. Actually, I'm going to, I'll go ahead and keep writing over here. The next number that's up is the 1/2. Now it's on the inside and it's being added, so that's a horizontal shift. It looks like it's negative 1/2, so it looks like it's going to be left 1/2. But it's on the inside, so it's the opposite of what it appears. It's not left 1/2, but rather right 1/2. So it's going to shift it right 1/2 unit. Not by a factor of a half. It's just picking it up, moving it over 1/2 unit, and setting it back down. And then the +3, which is the outside of the function, because it's outside the function now, it's affecting the graph vertically, the y values. Everything that's on the outside is exactly as it appears. So it's not down 3, but rather up 3. All right. So if you wanted to do this as a sequence of transformations, let me show you how that would look, because this is not necessarily how we're going to do it. But this is the way it would work. I'm going to draw the original function in kind of a mustard yellow. All right? If I vertically compress it by a factor of 2, that means that every y value is going to be twice as low as it used to be high. So now it's going to look like that. It's like you're taking the graph on either side of the x-axis and you're compressing it. All right, so now what I'm going to do, since we have notability, I'm going to get rid of the original function. I don't want it to be there anymore. But notice it's not as tall as it used to be. Now I am going to reflect it across the what axis? Y-axis, okay? So you take that mustard yellow graph and reflect it across the y-axis, and now it's going to open up to the left. So now I'm going to erase that one. So now we're on that step. Now you're going to compress it horizontally by a factor of 4. So this is what that looks like. All the x values are coming in 4 times closer. So when you're compressing, it's like you're grabbing it on either side of the y-axis, and it's like you're squeezing the accordion. Okay? That's going to effectively make the graph steeper again. See that? When you compress it horizontally, it effectively makes it steeper. But not by vertically stretching it, rather by compressing it horizontally. So I'm going to get rid of that graph now. So that's where we're left with. Now once you finish all the dilations and reflections, you have the final shape of your graph. It's going to look just like that. It might just be in a different location. Now I'm going to pick the graph up, and I could do that by lassoing it with scissors. I'm going to move it right a half unit. So there's a half unit to the right. There's 1/2, because that used to be at 0. And then up 3, no problem. Grab it, 1, 2, 3. And there's 3. So this is kind of cool with notability that we can do that. We can actually do it as a sequence of transformations. And there it is. There's what your final graph looks like. It's kind of nice on every parent function. They have like at least one point that you can kind of track and see where it goes. In this case, that was the original origin. It is now 1/2 to the right and up 3. Because stretching and compressing anything does not affect any point that passes through the origin, because it's 0 for both x and y. 0 times anything is 0. So there's what your new graph looks like. Now here's how I want you to think about sketching it. You can do it with notability like that and kind of erase the previous graph. But here's what I want you to be able to do. I want you to think about your parent function and say, okay, it's going to be half as tall, and then we're going to bring it in 4 times as wide. It's going to kind of keep the same shape, but it's going to be maybe a little bit steeper. But it's going to pretty much look like that. I'm never going to take out any kind of ruler and measure the steepness of your graph. So those are really hard to show on the graph unless you start labeling your y values, which you're not going to have to do. So a vertical stretch or compression and a horizontal stretch or compression, you're not going to have to show that. You're going to have to explain what happens, but you're not going to have to show that. So of those 3 things from the A and B, the reflection is the main one. It's now going to open to the left instead of to the right. So if you just think in your head, okay, it's going to come out of the origin and go off to the left. Now I'm picking it up and I'm moving it right 1/2 and up 3. So then you're just going to come here and you know the origin. Now move to 1/2, 3, and you're going to put that new point, and then you're going to draw it going up and to the left. And I am not going to care how steep or not steep that graph is. I'll extend the y-axis up. Okay? Now, if you are interested in another point that you can pick up relatively for free, what point do we have right here that's pretty easy to find? The y-intercept? Yeah. So if you want an extra point, let's go ahead and find the y-intercept. I might ask you to find it. Now, to show me that you're finding the y-intercept, to communicate that you're plugging in a 0 for x into the function h of x, you write h of 0. And I'm like, oh, you're plugging in a 0 for x into the function h. Cool. Now, I'm going to plug it back into the original one, not the transformed one. It would work. You could plug it into any version, but this one's just a little bit easier for evaluating. When you plug in a 0 for x, you get 3 plus 1/2 times the square root of 2. 3 plus 1/2 times the square root of 2, or 3 plus, that's the same as the square root of 2 over 2. Do we know what that number is without a calculator? Not really. But is the square root of 2 over 2, is it bigger than 1 or less than 1? Should be less than 1, right? Because the square root of 2 is smaller than 2. So if you take 3 and you add something less than 1 to it, it should be between 3 and what number? 4, right? It should be between 3 and 4. So you know your y-intercept is between 3, and I guess I'll just call that 4. Notice it's not to scale, but by putting values of 3 and 4, I know I've got it right. Okay? So there you go. We're done. Now that you have the graph, now we can start talking about it. What's the domain? All real numbers except the ones that don't work. So everything to the what of 1/2? Left. So it's the set of all x such that x is less than or equal to 1/2. Now let's say that you got your reflection wrong. You reflected it across the x-axis instead of the y-axis. If you reflect it across the x-axis, you're not going to have a y-intercept because it's going to open to the right. Finding the y-intercept then is a good check to make sure you have it open the correct way. Oh, and by the way, is this one that we know how to find the derivative of? Or I'm sorry, not the derivative, the domain of without the graph? Sure is. We practice this quite a bit. So let's go ahead and find the domain algebraically and compare it to what we got graphically. They should coincide with each other. We have a radicand, so remember you take the entire radicand, 2 minus 4x, and you say it has to be strictly, or greater than or equal to 0, sorry. Strictly non-negative, I guess you could say. And that's linear, so remember we can solve that algebraically. Negative 4x is greater than or equal to negative 2. And when we divide or multiply by a negative, we have to remember to not to forget to do what? Flip it. So now it's less than or equal to negative 2, negative 4th, also known as 1/2. Is that what we have for our graph? Yes. So that's another way to check yourself to see if you have the graph correct. But now that we know the domain is correct, we verified it, now we can answer the range question with a lot more confidence. Because the range we typically get from the graph. It's the set of all y such that y is greater than or equal to what? Three, right? The lowest y value on there is 3. We hit it because there's a solid dot there. We get nothing below it, but everything above it. This thing goes out to, as you go out to the left, it goes up to infinity. In other words, we can answer this now. The limit as x goes to negative infinity for h of x is what? Hop on the graph, start going out to the left. You're going to go up, 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 up to infinity. Yeah. Can you verify that by plugging in? Sure. Let's see. Let's see how that would look. Plug in a negative infinity for x. What's negative infinity times negative 4? Negative times negative is positive. We get positive infinity. 4 times infinity is infinity. What's infinity plus 2? Infinity, right. What's the square root of infinity? Infinity. What's half of infinity? Infinity. And infinity plus 3 is infinity. Yeah, so you could also do it that way. What would this be? What is the limit as x goes to positive infinity? Does this graph even have right-hand behavior? Does the graph live out here at infinity? Nope, it doesn't live to the right of 1/2. And 1/2, by no stretch of the imagination, is infinity. So this one is D and E. The right-hand behavior does not exist. Now remember, when you say that the limit is infinity, you're saying it doesn't exist also, but you're saying because the y values go up forever. Here when you say D and E, it's for a very different reason. Okay, does this function have any symmetry? Y-axis, x-axis, or origin? No, x-axis. We never looked for that one. Nope. Is this function monotonic? Monotonic what? Decreasing. Good. Over its domain. All right. Is there anything else you would like to comment or say about this function before we leave it forever? Kind of sad. You were good. You were good. For our first one, you were good. I'll always remember you. Our first. Okay. Example 4. We got like 4 minutes. Maybe we could do 4 something. 4a. Write the equations of the functions if the same transformations applied above are applied to the following parent functions. Oh boy. Okay. So if we took a different graph and we vertically compressed it by a factor of 2, reflected it across the x-axis, horizontally compressed it by a factor of 4, shifted it right 1/2 and up 3, what would the equation look like if we started with just a generic function y equals f of x? Well, here's what it would look like. We're going to take f of x, and let's kind of come up here. It's going to be a 1/2 out front, and instead of the square root, it's going to be f of, and then it's negative 4, parentheses, oops, let me put the parentheses there, x minus 1/2, close, close, plus 3. That's it. It's pretty much the exact same thing we have written right here in standard transformation form. The only difference is instead of the square root defining the function, we have f parentheses defining the function. So that's what it would be in general. So now what would it be for x squared? Well, the new function would be, what does it mean to be inside the x squared function? It means to be right there with the x before you square it. So that's going to be 1/2 parentheses, negative 4, x minus 1/2, close, close, squared, plus 3. So those transformations that we did above, they would do the exact same thing now to the starting graph of x squared. We're just starting with a different shape. Okay, you still got your outside, 1/2 and 3, outside the squared that is. And then inside the squared, you got your negative 4 and negative 1/2. So to be inside the squared function means to be happening on the x before you square it. What does it mean to be inside the 1 over x function? Where's the x? In the denominator. So to be inside this function means to be in the denominator. Let's do one more. This will be 1/2 parentheses, 1 over negative 4 parentheses, x minus 1/2, close, close, plus 3. We have outside the function, 1/2 and 3 still. Inside the function now, which means in the denominator, we got the same thing happening. Negative 4 times the quantity x minus 1/2. So that's going to do the exact same thing to that function 1 over x as we did to the radical function up above. We'll stop right there for today. We'll pick up at 4D tomorrow. Memorize your parent functions overnight if you don't already know them. That would be a good thing to do. And then we'll see y'all tonight at the Candlelight Pep Rally after the freshman game at dark 30.